So why is this so important? Well, this schematic has been presented in previous sessions, and I think this is quite a useful thing to look at, because if we're really describing endurance-based performance, we've already learnt that economy, the submaximal oxygen cost of exercise, is important. We understand that the VO2 max plays an important role. It's not fundamental, but it's an important role, and it determines really the ceiling for that capability. And then we understand that the lactate turn point, or as we're going to perhaps refer to it perhaps more readily here, the gas exchange threshold, that transition from aerobic to anaerobic based metabolism or moderate to heavy intensity exercise is crucial. But we now understand that this fourth parameter, the critical power, the ability to differentiate between what is going to be fatigue based exercise or limited exercise and actually exhaustive based exercise, and the boundary that it sets between the heavy and severe domains is crucial. All of these are linked to the oxygen uptake kinetics. This is why I'm saying if you haven't seen the session on oxygen uptake kinetics, it would be very, very useful to go and do that. And then they're all linked in themselves to the rate of carbohydrate oxidation, the rate of heat storage, the rate of decline or utilization of the anaerobic capacity, and then the rate of metabolite accumulation. So together, they determine exercise tolerance, and therefore determine both clinically and athletically the ability to exercise and produce power. So the critical power really sits at the heart of this, because it demarcates that fundamental boundary which we haven't really established yet. We've seen it in previous examples. We've seen the maximal lactate steady state, and we've seen respiratory compensation point, but we haven't understood the why behind this, and the critical power allows us to define the physiological why. So if we go a stage further forward and we take this data set that you can see here, so this is some data published, I'm just trying to look, this is Mark Burnley's data set, and what they've got here is you've got, again, power output on the X, oxygen consumption on the Y, and what you can see here we've got the lactate turn point, which is the boundary between moderate and heavy domain, so gas exchange threshold. And then they've got this parameter here, which we've learned in previous sessions is respiratory compensation point, or maximal lactate steady state, which is the boundary between heavy and severe. And this is really important to us. Remember that in the moderate domain, we can attain a steady state. That is, we can reach a steady state in oxygen consumption within around about 3 to 4 minutes, accepting that there will be a degree of drift both in cardiovascular and cardiorespiratory responses over time, primarily as a response of the process of thermogenesis. But we've got this second boundary which demarcates that boundary between heavy and severe. Now in the heavy domain we can attain a steady state, but it comes at an additional cost, and that is the development of the VO2 slow component. And if you remember, the VO2 slow component is a consequence of the recruitment of the less efficient type 2 muscle fibers. So the further we move into this domain, the more fast twitch fibers we've got to recruit. But we've then got this notion of non-steady state, unsustainable exercise, which is the severe domain. So severe really runs from critical power here up to VO2 max. So in that domain, no matter what happens, you will never attain a steady state. You will end up at VO2 max. You'll end up at the highest blood lactate concentration, and therefore the highest VO2. And then you go into extreme exercise, which is any exercise beyond the VO2 max, which is really that classic, in inverted commas, anaerobic or non-oxidative based exercise. And you can just see the difference here in the power output for these domains to a maximal power output response. So understanding this boundary between what is steady state and non-steady state exercise is really important, both in training prescription, but also if we're talking about race performance, and also in terms of our clinical population groups. Because we understand this responds to exercise, we understand this responds to training, as does this parameter here. So understanding how we identify this and why this occurs becomes really important. So we go a stage further, we can take the same graph, this is again from Mark Burnley's paper in 2016, and it just reinforces what we're referring to. So here's the moderate domain, and here you can see, again, that we've covered this in previous sessions on oxygen uptake kinetics. Here you can see the VO2 response. This is breath by breath data. And what you can see is a steady state has occurred. You can see the deficit at the onset here. So we've got a deficit, this is resting, so we start exercise here. There's a square wave transition. So the deficit here is relatively small and we get a steady state response. We now go into the heavy domain. So this is above the gas exchange threshold, but below the critical power. Two things that you'll notice, well, three things you'll notice. One is the oxygen cost is greater than in moderate. Two, the deficit is far bigger because the workload is at a higher intensity. The square wave transition is much greater. That is, the ATP turnover rate is much higher in the muscle. So the net result is we have a greater oxygen cost of exercise. But you'll also notice, and it's not perfectly clear, I will grant you, that there is this notion it's starting to level out, and then you suddenly get this slight acceleration here. So we're getting to a point of steady state, then it accelerates again, and that is the slow component. And the area under the curve represents the difference between the oxygen consumption that should have been consumed and the oxygen uptake that was actually consumed. And that is a reflection of type 2 fibre recruitment. But then you go above the critical power, and what you see here is three things. One, oxygen uptake is much higher. Two, the deficit continues to grow. Notice there is no steady state, and you end up terminating exercise far more quickly. Here they've got 20 minutes of exercise in both of these conditions, but they're terminating exercise in the severe domain within about 12 minutes, and this is VO2 max. So this boundary becomes really important to us, and you may make the case, well, okay, great, Dan, but why do we need to understand this if we can do maximal lactate steady state testing, or if we can do, for example, respiratory compensation points? Both very valid points. We understand the limitations with MLSS, which are generally methodological, time-based, very difficult to actually undertake, and you're still very much beholden upon what the increments in workload are that you're going to use to determine MLSS. The respiratory compensation point argument is one that is still open to debate. There are arguments and counterpoints to that argument about whether RCP really does correspond to either MLSS or critical power. I like to think that it probably does. I think there's a pretty good case to be made for it. But the critical power, as you're about to see, offers you so much more, because once you have this power duration curve, you can actually start to make significant predictions, but also start to prescribe training much more precisely than you could ever do with a respiratory compensation point. So the question is, why? Well, this is from a paper by Annie van Hattelo in 2007. And although I've highlighted key points, I'm going to read all of this because I think it's really important to our understanding. So she writes this: on the basis of the characteristic blood lactate and oxygen uptake responses during constant work rate exercise, three exercise intensity domains have been defined: moderate, heavy and severe. The boundary between the moderate and heavy domains can be established during incremental exercise testing using the lactate threshold or its gas exchange equivalent, gas exchange threshold, which is what we've been referring to. This threshold is important because it demarcates work rates for which a VO2 slow component is present, heavy, and severe exercise from those in which it is not. The boundary between heavy and severe exercise signifies the highest work rate at which a steady state can be attained. Work rates above the boundary result in VO2 and blood lactate rising as a function of time until the VO2 max is attained, with exhaustion occurring thereafter. Now, Annie makes a really important point. There is a clear distinction here between what is exercise which is being limited by fatigue and exercise which is being limited by exhaustion. And the critical power demarcates that. Once you move beyond critical power, the exercise limitation is exhaustion. And exhaustion is the accumulation of fatigue. You don't hit an exhaustion in the moderate and heavy domain. What terminates you is the fatigue in relation to the exercise domain. It's when you go into severe, you hit that point of volitional exhaustion, because fundamentally the fatigue is accumulating. It's the combination of the fatigues from all those metabolic mechanisms, all the accumulation of the metabolites, the decrease in the anaerobic capacity come together to produce the volitional exhaustion. And VO2 max. And now if we go a little bit forward, this is a paper from 2023 from Golding and colleagues. And this perhaps just goes a little bit further than Annie did in her paper, and they write this. However, above a particular individual specific power output, the consistent feature of exercise intolerance and hence impeding, excuse me, impeding task failure is the inability for pulmonary oxygen uptake and lactate to attain a steady state. Thus, for each individual, there exists a range of intensities for which a steady state in pulmonary VO2 is attainable, and a range for which it is not, with the duration of sustainable exercise in the latter being significantly limited compared with the former. And you saw that in that previous graph. In that previous graph, if we just flick back, oops, look at the difference. Here it's unsustainable. Now, bearing in mind, they would have asked the participants to terminate exercise at 20 minutes in this study here. Here, they weren't asked to terminate, they would have stopped at 12 minutes because the mechanisms of response are different. This is non-steady state exercise, they hit volitional exhaustion. Here, actually the exercise is much, much more sustainable, as you'll see further in this presentation. So what is the critical power then? How do we find it? Well, this isn't A.V. Hill, this is another Hill, this is Dave Hill from America. And I think it's quite a nice definition for us, which is, well, critical power or critical speed is the high submaximal exercise intensity that can be sustained without eliciting VO2 max. In other words, you go above critical power, VO2 keeps rising, irrespective of the workload above the critical power, to the VO2 max. If you're below the critical power, you're either in the heavy domain, or if you go way below it, you're in the moderate intensity domain. So the net result is, it provides this really important demarcation, this really important boundary for us between what is heavy and severe intensity exercise. It's a really nice, clear definition.